So hi everybody, it's our pleasure to have Andrea Lodi today to give our seminar. He'll talk about disjunctive cuts. We all know Andrea, so this will be a very short introduction. Andrea has, after his PhD, joined Bologna University, and then he came and spent a year with us at IBM. And since then we have been very good friends. He went back to Bologna, then Montreal, and finally we were lucky enough to recruit him to Cornell Tech. Andrea, the stage is yours.
Thank you. Thank you, Tai, for the friendship part. And I wanted to be fair with Omar and putting actually the mask on, but I don't think I'm going to do that. So it's my pleasure to actually be here, or actually I would like to be with you in the room in Ithaca. I'm still postponing my first visit as a faculty member, but I'm teaching Monday and Wednesday, so it would have been too much in a rush. But thanks for inviting me to give the talk. And this is joint work with Mathieu Tanot. That was my student in Montreal, and now he's at Georgia Tech as a postdoc, and Juan Pablo Vielma at the time in which we were working on this. He was at MIT, now is at Google now. So when I prepared the slides, I realized that, I mean, for the first version of the slide, that none of us were actually in the same place in which we were when we worked on this, but and we're still working on this. But I mean, in any case, when we first presented this in this paper. So let me talk about what getting into the material. So this is about mixed-integer conic optimization. So in mixed-integer conic optimization, I will assume to have a linear objective function and a set of conic inequalities, constraints. And in addition, the integer part comes from the fact that some of the variables are supposed to be integers, so take integer values. And so essentially what we are interested in this, the gray area is one of the constraints, but we are interested in actually finding the convex solve of this of the integer solutions of this problem. And this is called, indeed, we're referring to this as mixed-integer conic optimization, programming or optimization. In particular, what we are, I will talk about today is generating cutting planes for this mixed-integer conic problems. And I will first try to convince you that there are this, let's say, mixed-integer conic optimization, which is on the right here in the slides, and is a class, is a very large class in the sense that there are this is completely equivalent to the class of mixed-integer convex optimization. So mixed-integer convex optimization is doesn't assume to have a linear objective function, but of course you can always play the trick of putting the objective function as a constraint and using just a variable in that case, so the epigraph of it. So you're minimizing a non-linear objective function which has to be convex, and you are a set of convex constraints as well, non-linear convex constraints. So this is referred to as mixed-integer convex. And it is actually well known that you can transform any one of those into a mixed-integer conic optimization problem. And actually, there are results from Juan Pablo team that shows that you really need an handful of cones in order to do this. So essentially the second order cone is already giving you a lot, then the SDP cone, the semi-definite programming cone, and the exponential cone will be probably more enough to classify, to actually transform every mixed-integer conic optimization problem into at least 95% of them into mixed-integer conic optimization problems. So the reason why we are specifically interested into mixed-integer conic is that the conic duality is some sort of stronger, or gives us stronger tools in order to generate cutting planes. And this has been observed already before, it's not completely new, but we were going to try to explain why this is actually the case. So now very quickly, what is a cone? A cone is an object K, so script K in Rn is a cone if for every point and I take a lambda greater or equal than 0, lambda x is actually still belongs to the cone, and we have here 3 examples of cones. So the linear, the R2 plus, for example, on the left, we have the second order cone in the middle, and we have the exponential cone on the right. So the dual cone, and again, dualities. Dual cone is essentially obtained by taking any s in Rn and multiplying it by any point in x and still being non-negative. So, and being non-negative, s transposed x is actually non-negative. And this is the dual of my cone, original cone, and I will denote it as script of k star. So in addition, for conic inequality, I'm saying that this is a conic inequality x less or equal in conic form of y, which means that x and y, x minus y belongs to the cone. So valid inequalities. So what are we playing with? So we're playing with let's say, for disjunctive constraints, for those that are familiar in the audience with mixed integer linear optimization. Of course, disjunctive constraints comes through the idea of using, of course, extensively Farkas lemma. And here we're giving the intuition of what the Farkas lemma is in the conic context, not very different. So given a cone, I mean, a set of, a feasible set, which is given by x, ax, with the set of conic constraints ax greater or equal than b, and we have multipliers y, which belong to the dual cone, then I can produce any valid inequality by just doing a y transposed a times x greater or equal than y transposed b. So this is the extension of Farkas lemma essentially to the conic case. And what we are getting are all the possible inequalities for this set, for example, and these are the inequalities that I'm interested in. Of course, then I needed to use some sort of disjunction in order to cut off a fractional solution or solutions which are not fractional solutions or mixed integer solution that I don't like. And this Farkas lemma and this, it gives me always sufficient, is always sufficient to give me the equalities I want. It's necessary if capital A has full column rank. And the good news is that essentially, if I keep essentially using conic duality, I end up with inequalities that will make my AX greater or equal than B well posed. So well posed in this particular case, it means that either the system is strongly feasible or strongly infeasible, which again means that any non-polyhedral, for example, strongly feasible means that non-polyhedral conic inequalities are satisfied strictly. And this is actually very useful for avoiding numerical issues that I will try to discuss during the talk. So this is more or less the setting of the ground setting of my problem. And so if I go back to this at the beginning, so what I needed to do is that finding those blue inequalities that are actually defining at the intersection my corner point that is going to be the optimal solution of my problem. And in order to do that, as I said, I will try to use as much as possible conic duality and of course disjunctions in order to go. And in order to do that, the other tool that I need is split cuts. So what are the split cuts? I mean, the idea is quite simple. So I have a point x bar that I need to separate. So it's actually in the conic relaxation, but it's not integer. And so what I have to do is that I have to define an inequality by taking into account this disjunction. The disjunction here is defined by the pink part on the left and the blue part on the right, and everything that is in between, considering that x, if the disjunction is on the pi disjunction, pi transposed x less or equal than pi 0 is done as pi is integer and x and is non-zero on each one of the components of x that needs to be integer, then it's clearly true that whatever point is in between these two, say this split set, so pi transposed x less or equal than pi 0 and pi transposed x greater or equal than pi 0 plus 1 is not feasible for my problem, right? Because if the x is a vector of integer variables and pi is integer, then of course the combination of the two must be integer, and so must be either less or equal than pi 0, which is again another integer, or greater or equal than pi 0 plus 1. So what I want to do is I want to generate a cut by using this information. So if I have an x bar here that is not integer in all the components that needs to be to take integer value, then I can find the appropriate disjunction here, and I generate a cut that is called a split cut, or based on this split disjunction. So this lighter pink area is the split hole. So essentially, I'm cutting off everything that is in between, and the inequality that is coming out from this, ideally, would be a split cut. Okay, that is given by the intersection, the convex solve of the intersection of the convex solve of the union of the two conic sets that are obtained by imposing the split disjunction. So now, with this in mind, the idea is that I start with the mixed integer conic optimization problem. In this particular case, I'm saying that these are linear inequalities, a special case. These are linear inequalities, and x are belonging to a cone intersecting Zn. Then the split cut can be obtained in this form. So I want a split cut alpha transposed x greater or equal than beta, and is a valid inequality for the split disjunction, which is given by the system of before. So ax equal to bx in the cone, intersected by the one part of the disjunction, so the red or pink, whatever part here, pi transposed x less or equal than pi 0. And on the other side, it must be valid for the union of the other set, the blue part, ax equal b, x in the cone, and pi transposed x greater or equal than pi 0 plus 1. So in order to do that, I, again, will use the Farkas lemma in order to essentially finding an inequality that is valid for the union of these two guys. And in order to do that, I will extend the result by Balázs for the linear case. So linear case is actually the same case, except that x doesn't belong to a cone here, right? That's the only thing that changes here, is that x doesn't belong to a cone. So what I'm doing is I can find this cut by saying that I want, of course, the largest violation here. So I'm minimizing alpha transposed x bar minus beta, and I want this to be as small as possible. Essentially, this means that it will be a violated inequality. And I have to respect on this side the fact that I'm applying Farkas lemma on one side of the disjunction, and I'm applying the Farkas lemma to the other side of the disjunction. And if I put everything together, and so alpha and beta, of course, have to satisfy these things for both, then I'm actually in business. So here, a script of k star indicates the fact that I'm talking about the dual cone, and so this is the Farkas lemma applied to this. U are the multipliers, so the dual variables associated, and U0 is the multiplier associated to pi. Okay. Except that these are conic constraints at this point because of the fact that I'm considering k to be actually x belonging to k. So solving this is actually the first, let's say, result that we have into this research, in the sense that the mixed integer disjunctive cutting planes, so split cuts for mixed integer convex optimization have been let's say, designed for quite a long time. Starting from a seminal paper in the beginning of, I think it was in 1999 or maybe slightly later, by Stubbs and Merotra. And but here we are trying to take a much more let's say, conic, of course, approach based on the result that we were talking about at the beginning. So based on the idea that any mixed integer convex can be reformulated into mixed integer conic, strongly using conic duality. And this is actually the extension of the so-called cat-generating linear program by Balázs of the 70s, and to the conic case. So now, at this point, let me go back here. The dual, I can also write the
Andrea,
dual.
can I interrupt you for a second?
Of course,
just
yes.
Clarify. First, you had the disjunction at this point. So you have the two pieces. You're just trying to find a valid inequality given the disjunction.
Yes.
And second question is from Mike, actually. Mike thought he was asking if you need some sort of normalization.
Yes. 90% of the rest of my talk is going to be about normalization, Mike. So, absolutely, I do. So this cone is unbounded. And so essentially, if I solve it like this, I can minimize the violation as much as I want. This is exactly the same thing that happens in mixed integer linear programming. And indeed, I actually need the normalization. And I will try to convince you that based on the fact that I can do normalization on this cone, I can end up having a well-behaving system, which is not always the case when you are trying to solve directly, to generate directly convex, so disjunctive cuts for mixed integer convex optimization. But yeah, thank you very much for the question. So if I reformulate this problem that is in the slide now, you can see where I'm pointing, right? Can you? Or not?
Yes.
Okay, good. Thank you. So if I formulate this in the dual space, this is actually becoming the so-called the membership conic problem, and there's been a lot of literature in the last, let's say, 10 years on how to actually solving the membership conic problem and the cat directly in order to fast. Essentially, this has been implemented into Cplex, Gurobi, Express, everywhere, by using two types of approaches that I will talk about in a minute. So by combining essentially the work of Pierre Bonamy and the work of Key-Lynch, Linderoth, and Lutke. So essentially, again, my point is for understanding. So the algebraic representation of cuts with the Farkas multipliers and conic duality will make a difference. And from the computational standpoint, the difference is indeed that what we are proposing here is to directly solve the cat-generating conic problem. So there are, I've already talked about this, but I mean, the original paper of Stubbs and Merotra, I was right, 1999, was generating cuts for mixed integer convex optimization by solving a large NLP and then one LP. In order to derive the cuts itself. So like finding the condition on the NLP and then the LP for nailing down the cut. So this is relatively similar, but to what Pierre Bonamy did in 2011. So in his paper is doing, however, a sort of modified version of the NLP, just for retrieving conditions. And at that point, essentially, he is able to do some sort of outer-approximation. So he's using a cat-generating LP because he had some supporting hyperplanes for the cat itself. And by the way, I didn't say it explicitly, but I mean, it should be clear from, of course, it's clear maybe from this. The business here is that it's a mixed integer conic, so I have conic constraints, but what I'm concerned on is only on generating valid linear inequalities for my problem, okay? So there have been some attempts in the literature actually generating nonlinear inequalities, so convex inequalities for the problem, but so far from the computational standpoint, this is actually what has worked the best. So as I said, so in Pierre's approach, he uses a modified version of the NLP, and then he has this outer approximation scheme in which he is able to use one single cat generating LP, so large linear programming that he solves in the dual, so in the membership problem, while the approach by Killinch, Lutke, and Linderoth is solving a sequence of cat generating LP. So the idea is quite basic. I mean, it's quite simple but effective. So it's a sort of outer approximation scheme. So every time I'm trying to approximate my set with linear inequalities, and once I have the linear inequalities, I'm using it for building a cat generating LP that on the disjunctive set that is actually able to, and I check if I'm able to cut the point. If I'm not able to cut the point, then I refine my outer approximation and until I get what I want. So what you're doing here is more parsimonious, even if we're solving clearly a conic problem, so it's not trivial, but we are actually directly solving the cat generating a conic problem for generating for finding our valid inequality. So the neural normalization is indeed fundamental here. So the idea is how should I cut the cone? So in order that this is not unbounded and I'm actually able to define peak between the rays of this particular cone. So for the mixed integer linear in the linear context, that's exactly the same situation. And there's been extensive studies on this by especially on I mean, both on the theory and on the practical side. So on the theory side, so there is this nice and very influential paper by Balash and Peregard back in 2003, in which they show that the GMI cuts are actually split cuts. So every GMI cut is a split cut and is obtained by a particular normalization that leads to essentially to be solved, give extreme solutions of the cat generating LP. So GMIs can be mapped in the cat generating LP depending on the particular normalization that you're using. And then in a paper together with Matteo Fischetti and Andrea Tramontani back in 2011, we have actually analyzed extensively the effect of the various type of normalizations, so way of truncating the cone in order especially from the computational standpoint on sparsity, the rank of the inequality that you obtain, essentially the time for solving the problem itself, and of course at the very end what we care about is the gap closed. So how effective those inequalities are. So the domain again of the cat generating a conic problem is a cone, so there is no discrimination between the cuts, and truncated the feasible cone makes it bounded, and discriminate between the cuts, of course, has an impact on the obtained cutting plane, so that eventually will actually get stronger inequalities, and on the other end will also lead to keep some numerical quality on the overall scheme. That is, of course, more complicated than the classical linear programming context, and so this is essentially what we are gaining here. So the possibility of impacting the well-posedness and the solvability of the cat generating conic problem and the overall framework. So we have been testing in this work 5 different types of normalizations. And some of them are actually, the first 4 are essentially extensions of normalization that were already known in the context of the mixed integer linear programming problem. So the mixed integer linear context. And so the first one is the so-called alpha normalization. So the basic idea is to say, okay, in order to truncate the cone, what I'm doing is that I'm just saying that for any norm that I would like to use, and the L1 norm is the one that is used the most in that context, the alpha vector has to be less or equal than 1. Then I can do the so-called polar normalization. Polar normalization has been proposed by Balash and Peregard, indeed. So you take a convex combination, essentially, of, just gamma transposed alpha with gamma, which is a vector in Rn, and this is going to be less or equal than 1. So the standard normalization is actually the one, I have a typo here, so this is not exactly UMV. So this is more general, and this is lambda and mu. So what I have here is the standard normalization is simply the fact of taking all the multipliers that are involved in the sum of the multipliers according to some norm that is defined by using an interior of one point in the interior of the cone, and I'm summing everything, and I do it and I keep an upper bound equal to 1. So essentially, the idea that is a similar. It's just an extension on this norm to the of the mixed integer linear case, is that I'm just taking the sum of the multipliers and I'm using this for to be less or equal than 1. There is also the special case of this standard normalization is called the trivial normalization, in which I'm only taking the 2 multipliers which are associated with essentially the 2 constraints, the split in the split constraints. So essentially pi transposed x less or equal than pi 0, and pi transposed x greater or equal than pi 0 plus 1. Finally, the normalization that we are instead suggesting is the one that is actually removing, on the contrary, the two multipliers that are associated with this, and I actually only use the part that is associated with the conic inequalities. The reason I'm saying that is actually there's a typo here. That should be that in the notation that I used before, I was using AX equal than B, and these were linear inequalities. I don't need to truncate that part, to take into account that part in the normalization. I only needed to take into account the conic constraints. So there should be multipliers which are associated with the effect of X belonging to the cone, and that's why it's written in a different form. So this is essentially the standard. What we're going to see in a minute is in the computational part is that this actually normalization makes a huge difference, the use of the normalization, and the standard and the uniform normalization are actually the best, being more stable. But let me give you an intuition of what is going on here. So why this is so important. So this is actually a parametric example of solutions to be separated. And so parametric in the sense that this is the same split, right? I mean, in the 3 cases, except that the solution space is now in the first, so the leftmost A example is built in a way that there is the second part. There are 2 essentially conic sets, one on the left and one on the right. So in the second, in the middle, so B, my solution space is slightly different. So in gray, of course, we have the continuous relaxation, and the second constraint, so pi transposed x greater or equal than pi 0 plus 1, intersect this only in one point, which is actually here. while it's tangent to the space. And on the other side is actually there is no intersection. So I don't have a second part that is a second convex set. And depending on the normalization, I can get completely different cuts. For example, the trivial normalization, unfortunately, which is actually quite used still in the convex, in the linear case. So it's not, I mean, it's known not to be good, but not terrible, right? I mean, what the difference is now to be in the conic case is that this normalization becomes terrible, in the sense that the point that I'm trying to separate actually is not separated. So what I'm producing, I'm just producing what is an outer approximation cut. So it's a linearization cut in all three cases, is a linearization cut over passing by through x bar. So essentially using the trivial normalization is not effective at all. So it doesn't really produce the cuts I want. In the case, just to give you an example, of course, in the case of the uniform normalization for this particular example, I get what I really want in the A case, so something which is the best possible cut I could find. In the B case, it's not the strongest possible cut, and also in the C case, but they are, let's say, solid improvements in this very much cooked up example over, let's say, the trivial normalization, and the uniform normalization that turns out to be actually quite effective from the stability standpoint in our computational experiments. But I mean, this picture is mostly to actually give you an intuition of the difficulty of the impact of one normalization versus another can give in our ability to solve the cut generating conic problem.
Andrea, can I interrupt you one more time?
Of course, you can interrupt me as much as you want, Oktay.
Yeah. So back to figure 4 here, how is it possible that you cannot find a violated cut? It means that your cut generating conic program has an optimal value of 0, right? If it's not cutting the point.
Yes. Well, essentially, it becomes a numerical issue. It claims to have found a cut, but essentially the cut is not really like effective. So the violation is probably very, very minor, so it's very small, but essentially it doesn't really move.
Okay, it's a numerical issue.
Yeah, it's a numerical issue mostly, yes. So results. So what we did is experimental large computational setting. I mean, on 114 mixed integer second order cone problems that we found in the CBLib. And in addition, we have some other things in the paper, but I'm concentrating on those now. So I removed 13 instances. After this, actually, the 114, I think, is after removing 13 instances on which there were numerical issues or the root gap was actually very small. So to be able to appreciate anything. And the approach is that we are evaluating cut generating the conic problem plus the normalization, and what we use is as a baseline is simplex in the most aggressive in 2 different aggressive versions of the lift and project cutting planes for conic optimization. So simplex implements a combination of the approach by Bonamy and by Kilinch et al. And essentially, this is, as far as we know at this point, is one of the best ways of comparing and seeing the differences. So the metrics are the computing time, the gap, and the gap closed, and these are some results obtained with using only 10 rounds. So what does it mean, round of cuts? It means that in this, I mean, I'm not saying that in order to solve this synthesis, one should be completely aggressive cutting planes, possibly Cplex or Gurobi or Express will be able, or a specialized solver would be able to solve those instances faster without cutting planes, not in some situations. But here we are interested in seeing how good the cutting planes can be. And here we have on the 4 different algorithms. So the first one is a Cplex, in which we are indeed using 10 rounds of lift and project cuts. And alpha is the alpha normalization, so the first one, the standard normalization and the uniform normalization. We didn't test the polar, I'm not reporting results on the polar and on the trivial normalization. So here, what we are indeed interested in is the gap closed at the root node after this 10 rounds of cuts, and this is the CPU time. So the second column is CPU time. This is the group of the instances are belonging to different families, which if you some of the other, I think Oktay, you are familiar with those inequalities, with those constraints, which are uncapacitated facility location with quadratic objective function that you cooked up, I believe. And this is various other problems in the literature. So you can see that, red is bad and blue is good in this table. So what happens here is that Cplex in only 10 rounds of cuts is able to close, let's say, on average, 5.24% of the gap, but it takes a short amount of time, so just 1.5 seconds. So the alpha normalization is really not doing well, and it takes 16 seconds to actually close only 1.02% of the gap. In some situations, doesn't close any gap, even if there is some gap to be closed. So we don't know how much gap can be closed by essentially aggressive disjunctive cutting planes, because we are, eventually this is, we can go for a very, very big amount of separation rounds. But if we just give 10 and we are using the those normalization in order to discriminate, as we've seen before, which cuts I would like to use, then essentially this is what happens. So the standard normalization is doing pretty well. 17.97% of gap closed. In some particular context is doing great. So 93% of in this particular, for the SSSD instances, which is not even the best, because the uniform normalization can do 96.47. The uniform normalization, except for a couple of cases, like the Clay instances and the SLA instances, is performing very well, and indeed is closing 17.27. Both normalizations, standard and uniform, at this point are more or less equivalent. So, of course, it takes more time than Cplex. Well, this is not surprising in the sense that, of course, our code is solving, on the one side, is solving a conic optimization problems outside, so it's actually integrated through callback functions. So engineering wise, I think that there is some gap here, software engineering wise, but still is a quite reasonable amount of time for closing, in any case, at least three times more gap than what Cplex does. If I insist that I really want to solve this problem by cutting planes, these problems by cutting planes, then I'd be tempted to do with a much more aggressive setting, which is 200 of rounds of cuts. And we actually decided to have 200 rounds because I think that is the maximum that Cplex can be allowed to do. I think that is a parameter that is set into Cplex, the maximum amount of rounds that you can run. And as you can see, of course, Cplex gets much better. So it's 24% of gap closed, still takes a relatively small amount of time, but our two approaches are quite competitive, so we can get to 39. In particular, at this point, the uniform is doing better, and it gets actually to on average 39 0.13% of gap closed, which is 15% more in a computing time which is 65.5 seconds, which is roughly 6 times more than what the Cplex will take to generate those 200 rounds of cuts. So again, I would say that part of it is explained by the software engineering, let's say, quality of Cplex to be integrated directly into the code versus what we are doing. But overall, I think these are competitive and preliminary, but competitive results.
Andrea, as you allowed me to interrupt you at will.
Yes, please.
Now, to find these cuts, you have to start with a disjunction and then solve your cut-generating conic program using different normalizations. Where do you get the disjunction?
The disjunctions are by enumeration. So what by enumeration, in the sense that for every fractional variable that we have, we take all the possible cuts. So these are many cuts.
So it's like, xi greater or equal to 3, less than or equal to 2. So there's no, okay.
There is no, at this point, we were not interested in, I mean, of course, in any intelligence related to which disjunctions to use. But I mean, this is a good point. So essentially, one of the questions that we are asking ourselves is if there is actually a good way of selecting the cuts, even knowing that we are solving this type of problem. But
and
yes.
what does Cplex do? Do they also use single variable disjunctions in this?
This is single variable disjunction. These are lift and project cuts. Yes, single variable disjunctions. Yes. Yeah.
Thank you.
So wrap up. This is actually the preprint. We are currently revising it after the refereeing process in mathematical programming. So on the contribution side, there is more in the paper that I decided not to actually spend the time on very much. We are actually doing for the first time lifting, strengthening, and some analysis on the sparsity of the cuts itself. That is, the lifting and the strengthening are quite new in the context of mixed integer conic. The results, I would say, that are promising in terms of if for the people in the audience, maybe you, Tai, as well, especially that familiar with this 20 years of attempt on let's say using disjunctive cutting planes in the context of mixed integer convex or conic, starting from of course extending the results of Balázs for the linear case. The difficulty on, Merotra Stubbs' paper in 1999 was essentially saying, oh, this is mostly hopeless because the NLP that has to be solved is very nasty and very difficult from the numerical standpoint. So there have been a lot of studies related to this. For 15 years, almost 15 years, nobody tried anymore to do it. Then Pierre Bonamy jumped into this and looked at essentially both for the linear and for the non-linear case, looked at the membership problem and found very good results. But I mean, in all these papers, there are some nasty examples that are showing the difficulty of doing that and of doing this separation. And we think that what we are doing, so we analyze in the paper many of those examples, and we essentially, of course, it's not the end of the story in the sense that we still have numerical difficulties on problems in which we have to essentially doing some let's say special tricks for make it working. But overall, our takeaway is that the conic formulation is actually helping a lot in being able to deal with most of the numerical issues that you can find. And of course, there are a bunch of other open questions. So some of them have been looked at by Mathieu by himself when he joined Georgia Tech. So he's is looking at, for example, facial reduction in order to actually being able to avoid even solving the conic problem, but actually projecting it into a linear context by doing facial reduction. I think this is a very interesting way of approaching the problem, and I think Mattia gave a talk in the Mixed Integer Nonlinear Programming conference that there was, I believe, earlier this year. So if you, I think the talk is on YouTube and is quite interesting. We have scaling questions to be looked at, the sparsity and fast separation rules somehow is connected to this facial reduction. But on the other end, there are, of course, the decision of which type of disjunction you would like to use that Oktay was pointing out is a very fundamental question. And I think I'm stopping here. Thank you.
Thank you. Questions? Questions from Zoom? So then I'll ask one more question, Andrea.
Yes.
So in terms of solving the integer program to optimality, do these cuts help? Do they speed up the solution time? Did you experiment with that?
We did a few, let's say, experiments on essentially using, I mean, on using the cuts in the tree as well, and also clearly in try to let's say fix the formulation at the end of these 200 rounds and running. It really depends very, very much on the problems and the group of problems that we were looking at. And so it's still, I still don't have a very, very clean answer on this. Sometimes they do, sometimes not really very much. And we don't really understand what is, if there is a pattern associated with that. So it's a, you know, there's been quite a lot of work also for in the convex case for nonlinear constraints like the work of Alper and others who MIR conic inequalities or things like this, in which you strengthen the formulation at the very beginning and then you run your favorite solver. The results are more or less mixed, in my opinion. So it's not clear that we don't see yet, let me say in this way, we don't see yet the pattern that we have in mixed integer linear for which cutting planes are making the entire difference.
Thank you. Any other questions? Okay, Andrea, thank you very much. Oh, Mike?
Yeah, I was just going to say you showed two tables, one with 10 rounds, one with 200. And I didn't see the numbers closely enough, but the Cplex rounds are much, much cheaper. So if you did 100 rounds of Cplex, how would that compare to 10 rounds of uniform in terms of gap and time?
Well, my impression, it's a good question. So I think we tried more or less a lot of different things. I think Cplex in some particular situation. So for example, you can see that here is doing very well, right? I mean, take this SSSD. So this is a 45% in only 10 rounds, while our approach is going immediately to 93 in 10 rounds, but then Cplex is able to catch up, right? I mean, it gets to 95 in these 200 rounds. So it's closing the gap, right? I mean, it's doing much better. So I don't have a picture in mind exactly on when this happens, but I think it's gradually going up, so it's not jumping very, very much. I think that the good news here, for example, for this SSD, is that sometimes the cuts are are very effective pretty quickly, and so which means that potentially is the way in which they are separated makes a difference. But I'm expecting that over time, even what's in Cplex, what is done into Cplex will lead to the same results. So I think it's a good idea to also look at what happens in the 200 iterations or rounds or many more. It's a good question. Yes.
Thanks.
Any other questions? Okay, in that case, thank you very much, Andrea, and we all look forward to seeing you here in person.
Yes, that would be my pleasure. Thank you, guys.
Thank you.